Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The flow of electricity, invisible yet undeniably present, posed a fundamental challenge to the nascent science of the early 19th century. Early experimenters, captivated by the mysterious forces at play, struggled to quantify the ebb and flow of this novel phenomenon. Unlike the well-established realms of mechanics or optics, electricity lacked a cohesive mathematical framework, a set of guiding principles that could predict its behavior with precision. Before Georg Ohm, the understanding of electrical circuits, often referred to as galvanic circuits after Luigi Galvani's pioneering work, remained largely qualitative. While the effects of electricity were observable, the twitch of a frog's leg, the spark of a discharge, the precise relationships governing current strength, the driving force, and the impediments to its passage remained shrouded in uncertainty. The limitations of the experimental apparatus of the time further compounded the difficulties. Early electrical investigations relied on voltaic piles, clumsy and often unreliable sources of electrical potential. These piles, constructed by Alessandro Volter, offered a means to generate a sustained current, but the fluctuations in their output, the difficulty in maintaining a stable voltage, and the imprecision inherent in the available measuring instruments all conspired to frustrate attempts at rigorous quantification. Measuring the intensity of the current itself was a significant hurdle. Early experimenters frequently relied on the deflection of a magnetic needle, a crude proxy for the flow of charge. This approach, while providing a qualitative indication, lacked the sensitivity and accuracy required for precise measurements. The absence of a standardized system for quantifying the electrical properties of materials hampered the development of a predictive theory. The concept of resistance, the property of a material to impede the flow of current, was poorly understood, and its relationship to other electrical quantities remained unexplored. Into this environment of experimental and conceptual challenges stepped Georg Ohm. His ambition was to bring order to the chaos, to establish a rigorous, quantitative understanding of the electrical circuit. He sought a mathematical description, a set of equations that would precisely relate the measurable quantities of voltage, current, and the properties of the conducting materials. His initial experiments, undertaken in 1836, marked a decisive turning point in the history of electricity. Ohm's work was a paradigm shift, a move from the descriptive to the predictive. Ohm's experimental setup, a testament to his ingenuity and persistence, involved a voltaic pile as a source of electrical potential, a galvanometer to measure current, and carefully prepared copper wires of varying lengths and cross-sections. He meticulously constructed his apparatus, recognizing the importance of precision in every detail. The voltaic pile, although a relatively crude device, provided a sustained source of electrical force. The galvanometer, a device that measured current by the deflection of a magnetic needle, served as the primary instrument for quantifying the flow of electricity. A central challenge Ohm faced was the instability of the voltaic pile. The voltage produced by the pile varied over time, introducing significant error into his measurements. To address this, Ohm implemented several strategies. He carefully calibrated his voltaic pile, monitoring its output over time and accounting for any fluctuations. He also made efforts to maintain a consistent temperature, recognizing that temperature variations could affect the resistance of the wires. Temperature control was a crucial factor, as he understood that the electrical properties of the conducting wires were sensitive to changes in temperature. Ohm's earlier experiments involved measuring the current through copper wires of different lengths. He systematically varied the length of the wire while keeping the voltage constant, observing the corresponding changes in the current. He also investigated the effect of varying the cross-sectional area of the wire and the influence of different materials. His work was not a simple exercise in data collection. It was a carefully planned and executed investigation, guided by a clear theoretical objective. The initial reception to Ohm's findings, unfortunately, was far from enthusiastic. His work, initially published in 1836, met with skepticism and even outright rejection from some of the leading scientists of the time. The prevailing scientific community, steeped in established traditions, found his focus on mathematical formalism unfamiliar and perhaps even unsettling. The idea that electricity could be described by a simple mathematical equation was a departure from the prevailing qualitative understanding. Ohm's use of a torsion balance, an instrument used to measure the force between charged objects, reflects his dedication to precision and his desire to validate his experimental findings. The torsion balance allowed him to measure the electrostatic force between charged bodies, providing an independent means of confirming his observations. He used this instrument to establish a relationship between the electric force and the distance between charged objects. From his meticulous experiments and painstaking analysis, Ohm formulated a fundamental relationship, a mathematical expression that would become known as Ohm's law. This law, a cornerstone of electrical theory, states that the current I flowing through a conductor is directly proportional to the voltage V applied across its ends and inversely proportional to the resistance R of the conductor. The law is expressed mathematically as V equals I times R. This simple equation encapsulated the essence of his discovery, providing a precise and predictive framework for understanding the behavior of electrical circuits. It was a breakthrough, a concise statement that unified the previously disparate observations into a coherent and quantifiable whole. The law provided a foundational basis for the study of electricity and laid the groundwork for the development of modern electrical engineering. Having established a framework for understanding the electric force, Georg Ohm turned his attention towards the precise measurement and quantification of electrical current. The challenges he faced were considerable. The tools available for measuring electrical phenomena in the early 19th century were rudimentary. Galvanometers, devices that detected and, to a limited extent, measured current, were the primary instruments. However, these instruments were often unreliable, susceptible to environmental fluctuations, and lacked the precision necessary for rigorous scientific investigation. Ohm's genius lay not only in his theoretical insights, but also in his meticulous experimental design and unwavering commitment to accuracy. Ohm's experimental approach was characterized by a systematic and rigorous methodology. He recognized the importance of controlling variables and isolating the effects of different factors on the flow of current. A key element in his experiments was the use of a voltaic pile, a predecessor of the battery, which provided a consistent source of electrical potential. However, the output of these early electrochemical devices was inherently unstable, varying with temperature and and the consumption of the chemical reactants. To mitigate these fluctuations, Ohm devoted considerable effort to stabilizing his voltage source. He paid close attention to the composition of the pile and the materials used, striving to maintain a relatively constant voltage output throughout his experiments. The heart of Ohm's experimental setup was the circuit itself. He employed a variety of conducting wires, varying both their length and their composition. He understood that the properties of the conductor would significantly influence the flow of current. He carefully selected different materials, including copper, silver, and iron, and meticulously measured their dimensions. He realized that the length of the wire was a crucial variable, and he systematically varied it, recording the corresponding changes in current. These measurements were instrumental in establishing the relationship between wire length and resistance. Temperature was another critical factor that Ohm sought to control. He understood that the resistance of a conductor changed with temperature. To minimize the impact of temperature variations, he conducted his experiments in a stable environment and took steps to ensure that the wires remained at a relatively constant temperature. He did this by allowing the wires to equilibrate to the ambient air temperature before taking measurements. This attention to detail, though seemingly minor, was essential for achieving the accuracy he sought. To measure the current, Ohm relied on galvanometers. However, the early galvanometers were far from ideal. They were often based on the deflection of a magnetic needle, with a degree of deflection intended to be proportional to the current. The sensitivity of these instruments varied, and their readings were affected by external magnetic fields. Ohm addressed these limitations by calibrating his galvanometers carefully. He used a standardized method to establish a relationship between the deflection of the needle and the actual current flowing through the circuit. He created a series of known currents, perhaps using different voltaic piles or varying the resistance in the circuit, and recorded the corresponding deflections. This calibration process allowed him to convert the galvanometer readings into quantitative measures of current. Ohm's experimental data were meticulously recorded and analyzed. He generated extensive tables of measurements, meticulously documenting the voltage, wire length, wire material, and the corresponding current readings. He then sought to identify patterns and relationships within this data. This was a painstaking process, requiring both careful observation and a keen understanding of the underlying physics. His analysis was heavily influenced by the work of Joseph Fourier, whose work on heat conduction provided a conceptual model for Ohm. Fourier's work, theory analytique de la chaleur *1/832, presented a mathematical framework for describing the flow of heat through materials. Fourier developed differential equations to model this phenomenon. Ohm, drawing parallels between heat flow and electrical current, adapted Fourier's mathematical techniques to analyze the flow of electricity. He recognized that the current flowing through a conductor was analogous to the flow of heat through a material, with voltage playing the role of temperature difference and resistance acting as a measure of the material's opposition to current flow. Ohm used this analogy to formulate a mathematical model for electrical circuits. He hypothesized that the current was proportional to the driving force, voltage, and inversely proportional to the resistance of the circuit. He then used his experimental data to test this hypothesis and refine his model. His work was not a simple matter of curve fitting. It involved a conceptual leap, a profound understanding of the underlying physics, and a rigorous application of mathematical principles. One of the key concepts Ohm explored was the intensity of the current. He defined this intensity as the amount of charge flowing through a cross-section of the conductor per unit of time. This definition, while seemingly straightforward, was a crucial step in quantifying electrical phenomena. It allowed him to relate the macroscopic properties of the circuit, such as voltage and resistance, to the microscopic behavior of the electric charge carriers. This was a significant advance, paving the way for a deeper understanding of electrical phenomena at a fundamental level. To illustrate Ohm's approach, consider a simplified example based on his published data. Imagine he experimented with a copper wire of a specific cross-sectional area and temperature. He varied the length of the wire and measured the corresponding current using his calibrated galvanometer. His data might have looked something like this: wire length Cn, current arbitrary units 10, 10, 25, 33.33, 42.5. From this data, Ohm would have observed an inverse relationship between wire length and current. He would then have calculated the resistance, which he defined as the ratio of voltage to current. He would have found that the resistance increased with the length of the wire, demonstrating a fundamental property of electrical conductors. The systematic and quantitative approach Ohm championed was revolutionary. Before his work, electrical phenomena were primarily studied qualitatively. There was an understanding of static electricity and the effects of electric shocks, but there was no precise way to measure or predict the behavior of electric circuits. Ohm's work changed that. He established a quantitative framework based on careful measurement and mathematical analysis that allowed scientists and engineers to understand and manipulate electrical circuits. A legacy of his experimental methodology is profound. It established the importance of controlled experiments, accurate measurements, and the rigorous application of mathematics in the study of electricity. It set a standard for scientific investigation that continues to influence the field of electrical engineering and beyond. Ohm's most significant contribution, the one that secured his place in the pantheon of scientific giants, was the formulation of what is now universally known as Ohm's Law. This law, expressed mathematically as V equals IR, provided a precise and quantifiable relationship between three fundamental electrical quantities: voltage, current, and resistance. The genesis of Ohm's law stemmed from the need to understand the behavior of electric circuits in a systematic way. Prior to Ohm's work, while the qualitative effects of electricity were known, the shocks from Leyden jars, the attraction and repulsion of charged bodies, there lacked a framework for predicting with any degree of accuracy how electricity would behave in a closed circuit. The conceptual leap Ohm made was to relate these electrical properties mathematically. He didn't simply observe phenomena, he sought to describe them with equations, bringing a level of mathematical precision previously unseen in the study of electricity. The equation itself, V equals IR, appears deceptively simple, yet it encapsulates a profound understanding of how electricity flows. V represents voltage, the electrical potential difference that drives the flow of charge, analogous to the pressure that drives water through a pipe. I represents current, the rate of flow of electric charge measured in amperes. Finally, R represents resistance, the opposition to the flow of current measured in ohms. The equation states that the voltage across a conductor is directly proportional to the current flowing through it, with the constant of proportionality being the resistance. This means that if the voltage increases, the current increases proportionally, assuming the resistance remains constant. Likewise, if the resistance increases, the current decreases for a given voltage. Ohm's experimental approach was crucial in establishing this relationship. He meticulously measured the current flowing through different lengths and thicknesses of wires, varying the voltage applied across them. Through these experiments, he observed that the current was directly proportional to the applied voltage and inversely proportional to the resistance of the wire. The precise measurements, coupled with the mathematical formulation, provided a predictive tool for circuit analysis. This allowed engineers and scientists to calculate with reasonable accuracy the current flowing through a circuit, given the voltage and resistance. Ohm applied his law to various circuit configurations. While his work predated the formalization of circuit theory as we know it today, he explored series and parallel connections. Though the specifics of his analysis are less well documented than the general law itself, he demonstrated how the total resistance in a series circuit increases as additional resistors are added, while the total resistance in a parallel circuit decreases. This understanding, even in its nascent form, laid the groundwork for the more complex circuit analysis that would follow. It is important to note that Ohm recognized the limitations of this law. He understood that the law applied primarily to metallic conductors under constant conditions. He was aware that resistance could change with temperature and that the law might not hold for all materials or under all conditions. He was careful to qualify his findings, acknowledging that the relationship between voltage, current, and resistance might be more complex in certain situations. The immediate impact of Ohm's work on the development of electrical theory was substantial, even though it was initially met with skepticism. It provided a framework for understanding and predicting the behavior of electric circuits, moving the field from a collection of empirical observations to a science based on quantitative relationships. Ohm's work provided a foundation upon which others could build, leading to the development of more complex circuit analysis techniques and the design of more sophisticated electrical devices. The initial reception of Ohm's law within the scientific community was far from enthusiastic. The primary criticism centered on the perceived lack of theoretical basis for his findings. Many scientists of the time were accustomed to a more qualitative approach to electricity, emphasizing the nature of electrical fluids or the effects of electrical forces rather than a focus on mathematical relationships. Ohm's work, with its emphasis on precise measurement and mathematical formulation, was seen as overly abstract and divorced from the underlying physical mechanisms. One of the most vocal critics was Georg Ohm's former teacher, Professor Johann Schweger, a prominent physicist in Germany. Schweger, who had previously been a supporter of Ohm's experimental work, now viewed his former student's law with suspicion. He, along with other established scientists, questioned the validity of the equation and the methods Ohm used to derive it. The resistance came from the prevailing scientific culture, which prioritized qualitative descriptions and theoretical frameworks over quantitative analysis. Ohm's approach, which relied heavily on experimentation and mathematical modeling, was considered by some to be a distraction from the fundamental questions about the nature of electricity. The debates and controversies surrounding Ohm's findings highlighted the role of mathematical rigor in the study of electricity. Ohm's insistence on quantifying electrical phenomena challenged the prevailing views and forced scientists to reconsider the importance of precise measurement and mathematical analysis. The existing understanding of electrical phenomena at the time was largely based on the work of earlier pioneers such as Charles Augustin de Coulomb and Alessandro Volta, whose work focused on static electricity and the generation of electricity, respectively. Ohm's work, which focused on the flow of electricity in circuits, offered a new perspective that challenged the established framework. The work of Jean-Baptiste Biot and Félix Savart, though predating Ohm's law, provided crucial foundations for the development of electromagnetism. Biot and Savart, through their experiments, established a relationship between the electric current and the magnetic field that generates. Their findings, known as the Biot-Savart law, demonstrated that a current-carrying wire produces a magnetic field around it, and the strength of this field is directly proportional to the current. Ohm's work, while focused on the relationship between voltage, current, and resistance, built upon the understanding of electromagnetism established by Biot and Savart, providing a framework for analyzing electrical circuits and predicting their behavior. Ohm's work did not directly improve upon the Biot-Savart law, as it was focused on the electrical properties of circuits rather than the magnetic properties of current-carrying wires. However, his work complemented theirs by providing a means to quantify and predict the flow of electricity, which is essential for understanding the generation and use of magnetic fields. The eventual acceptance of Ohm's law, a process marked by both resistance and eventual triumph, fundamentally reshaped the landscape of electrical science. The initial skepticism, born from the prevailing scientific climate and the limitations of experimental techniques, gradually yielded to a growing consensus. This shift was propelled by a confluence of factors: improved experimental practices, the development of more precise measuring instruments, and, crucially, the theoretical frameworks that built upon Ohm's foundational work. A critical figure in the validation and expansion of Ohm's discoveries was Gustav Kirchhoff. Kirchhoff, a German physicist, built upon Ohm's framework, formulating his circuit laws. These laws, which elegantly describe the conservation of charge and energy within electrical circuits, provided a powerful tool for analyzing complex networks. Kirchhoff's first law, the current law, states that the algebraic sum of currents entering a node or junction in an electrical circuit equals zero. His second law, the voltage law, states that the algebraic sum of the potential differences or voltages around any closed loop in a circuit is zero. These laws, directly derived from and consistent with Ohm's law, allowed for the systematic analysis of circuits with multiple components, providing a predictive power that extended far beyond the simple circuits Ohm initially investigated. Kirchhoff's work, published in his seminal papers on circuit analysis, demonstrated the universality and applicability of Ohm's principles. His laws were a direct consequence of Ohm's work and provided a critical foundation for the development of electrical engineering. Kirchhoff's methods enabled engineers to predict the behavior of intricate electrical systems, from telegraph networks to early electrical lighting systems. The influence of James Clerk Maxwell, though indirect in some respects, further solidified the standing of Ohm's work within the broader scientific community. Maxwell's groundbreaking work on electromagnetism, culminating in his famous equations, unified electricity and magnetism, demonstrating that light itself is an electromagnetic wave. While Maxwell's equations addressed the behavior of electromagnetic fields, they were entirely consistent with Ohm's law. In fact, the law provided a crucial component for understanding the behavior of electrical circuits within Maxwell's framework. Maxwell's work, therefore, provided a theoretical context that demonstrated the consistency of Ohm's law with the fundamental laws of electromagnetism. Maxwell's unification of electricity and magnetism reinforced the validity of Ohm's empirical observations, solidifying its place as a cornerstone of electrical science. The evolution of experimental techniques and the refinement of measuring instruments played a crucial role in the widespread acceptance of Ohm's law. Relative experiments, hampered by imprecise measuring tools and the challenges of controlling experimental conditions, often yielded inconsistent results, contributing to the initial skepticism. However, as scientists improved their ability to measure electrical current, voltage, and resistance with greater accuracy, the validity of Ohm's law became increasingly apparent. The development of more sensitive galvanometers, devices used to measure electric current, allowed for more precise measurements. Furthermore, advancements in battery technology, providing a more stable source of electrical potential, also contributed to the reliability of experimental results. These improvements allowed researchers to repeatedly demonstrate the linear relationship between voltage, current, and resistance as described by Ohm's law under a wide range of conditions. Ohm's own publication, Die Galvanische Mathematische Verbete 1957, served as a crucial platform for disseminating his findings, promoting his mathematical approach to electrical phenomena. This work, a testament to Ohm's dedication to rigorous mathematical modeling, presented his law in a clear and concise mathematical form. The book, despite facing initial criticism, eventually gained recognition for its groundbreaking approach to understanding the behavior of electrical circuits. The mathematical framework provided by Ohm allowed for quantitative understanding of electrical phenomena, paving the way for the development of electrical engineering as a distinct discipline. The practical implications of Ohm's law quickly became evident in the burgeoning field of electrical technology. The development of telegraphy, one of the earliest practical applications of electricity, was directly dependent on a clear understanding of the principles governing electrical circuits. Ohm's law provided the essential framework for designing and analyzing telegraph circuits, enabling engineers to optimize the transmission of electrical signals over long distances. Engineers could now calculate the appropriate resistance for wires and the voltage required to transmit signals effectively. This led to the development of more efficient and reliable telegraph systems, which revolutionized communication. The impact of Ohm's law on the development of the first electric circuits was profound. Before Ohm's work, the understanding of electrical circuits was largely based on qualitative observations and empirical rules. Ohm's law provided a quantitative framework for analyzing the behavior of these circuits, enabling engineers to design and build more complex and efficient electrical devices. This was particularly important in the development of early electrical machines, such as electric motors and generators. The ability to calculate the current, voltage, and resistance in these circuits was essential for optimizing their performance and ensuring their safe operation. The law also paved the way for a deeper understanding of electrical power and energy. By establishing the relationship between voltage, current, and resistance, Ohm's law laid the groundwork for understanding how electrical energy is converted into other forms of energy, such as heat and mechanical work. This understanding was crucial for the development of electrical power systems, which would eventually transform society. Engineers could now calculate the power dissipated in a circuit, enabling them to design more efficient and safer electrical systems. The lasting impact of Ohm's work extended far beyond the realm of pure science. It provided the foundation for the development of electrical engineering as a distinct discipline. The ability to mathematically model and predict the behavior of electrical circuits was essential for the development of a wide range of electrical technologies, from electric lighting to telecommunications. Ohm's law provided the fundamental principles that engineers used to design and build the electrical systems that powered the Industrial Revolution and continue to shape our modern world. The law's enduring legacy is a testament to its fundamental importance in the history of science and technology. Ohm's work, therefore, stands as a landmark achievement, a testament to the power of combining experimental observation with rigorous mathematical analysis. The profound significance of Georg Ohm's endeavors resides not merely in the formulation of a single empirical law, but in its profound implications for the very fabric of scientific inquiry. His work, meticulously weaving together experimental observation and mathematical modeling, reshaped the landscape of electrical science, establishing a paradigm that continues to resonate throughout the scientific community. The elegance of Ohm's law, a simple expression relating voltage, current, and resistance, belies its revolutionary impact. It offered a precise, quantifiable framework for understanding electrical phenomena, enabling engineers and scientists to predict and manipulate electrical circuits with unprecedented accuracy. The ability to mathematically describe and predict electrical behavior proved transformative. Prior to Ohm's insights, electrical experimentation was often a realm of empirical observation, characterized by trial and error. The absence of the unifying mathematical framework hindered the development of reliable electrical technologies. Ohm's law, however, provided the crucial missing link, transforming electrical science from a collection of disparate observations into a coherent, predictive discipline. This shift facilitated the design of more efficient and reliable electrical devices, paving the way for the technological advancements that would reshape society. The influence of Ohm's work is readily apparent in the evolution of the scientific method itself. His unwavering commitment to rigorous experimentation, coupled with his adeptness at applying mathematical principles, served as a model for future generations of scientists. Ohm meticulously designed and conducted experiments, carefully measuring electrical quantities and systematically varying parameters to uncover the underlying relationships. His approach emphasized the importance of quantitative data and mathematical analysis, establishing a standard for scientific investigation that remains relevant today. The meticulous nature of his experiments, documented in his seminal work, Die Galvanische mathematisch Bearbeitet asterisk, exemplify the power of a systematic approach to scientific inquiry. The legacy of Ohm's work extends to the very foundations of electrical engineering. The ability to design and analyze electrical circuits with precision was a direct consequence of Ohm's law. Engineers could now calculate the current flow, voltage drops, and power dissipation within a circuit, allowing them to optimize designs for efficiency and safety. This newfound ability to predict circuit behavior enabled the development of a wide array of electrical technologies, from electric lighting to telecommunications systems. The Industrial Revolution, driven in part by the advent of electrical power, owed a significant debt to Ohm's fundamental contributions. His law provided the crucial mathematical framework that allowed engineers to harness the power of electricity, transforming factories, transportation, and communication systems. The enduring relevance of Ohm's work lies in its fundamental nature. While specific technologies may evolve, the underlying principles governing electrical circuits remain unchanged. Ohm's law continues to be taught in introductory physics and electrical engineering courses worldwide, serving as an essential foundation for understanding more complex electrical concepts. The law's concise and elegant formulation has withstood the test of time, serving as a testament to its fundamental importance. It remains an indispensable tool for engineers, physicists, and anyone seeking to understand the behavior of electrical circuits. The historical context of Ohm's work is equally significant. He labored during a period of intense scientific ferment, a time when the scientific revolution was gaining momentum. The prevailing scientific ethos emphasized experimental observation and the application of mathematical principles to explain natural phenomena. Ohm's work perfectly embodied these ideals. He embraced the experimental approach, meticulously gathering data and applying mathematical tools to unveil the underlying principles governing electrical circuits. His contributions aligned with the broader goals of the scientific revolution, which sought to replace speculative philosophical explanations with empirically grounded, mathematically rigorous theories. The impact of Ohm's work extends far beyond the realm of electrical science. His emphasis on rigorous experimentation and mathematical modeling influenced the development of other scientific disciplines. The meticulous approach he employed, the careful collection of data, and the application of mathematical analysis served as a model for scientists in all fields. The enduring influence of Ohm's work can be seen in the development of modern technologies. From the microchips at the heart of modern computers to the complex electrical systems that power our societies, Ohm's law remains an essential principle. The profound significance of Ohm's work lies in its ability to bridge the gap between the abstract world of mathematics and the tangible reality of electrical phenomena. His law provides a precise, mathematical description of electrical behavior, allowing scientists and engineers to predict and manipulate circuits with remarkable accuracy. The marriage of experimental observation and mathematical modeling, a hallmark of Ohm's approach, transformed electrical science, ushering in an era of unprecedented technological innovation. The enduring legacy of Georg Ohm is a testament to the power of perseverance, rigorous experimentation, and the unwavering pursuit of scientific truth. His contributions provided the fundamental principles that shaped the modern world. His work exemplified the importance of mathematical rigor and experimental validation in the advancement of scientific knowledge. His law serves as a reminder of the enduring value of scientific inquiry, and its impact continues to reverberate through the scientific community. The technological advancements that define our modern world, from the simplest electronic devices to the most sophisticated technological systems, owe a profound debt to Ohm's groundbreaking work. In conclusion, Georg Ohm's profound legacy is a beacon, illuminating the path for future generations of scientists and engineers. His law, a seemingly simple equation, has fundamentally altered our understanding of the electrical world. It remains a cornerstone of scientific knowledge, a testament to the power of human ingenuity, and a reminder of the enduring significance of the scientific method. His work continues to shape our understanding of the electrical world, even if not directly applicable in the modern world, providing the foundation for countless technological advancements that define the modern world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.